Okay, lecture 6, our last lecture before the 3-day weekend, and I'll tell you that I have a homework for you that's due Wednesday, but I don't think I did the whole, I have 5 days, let's see how much work I can cram into those days. I think that this homework is no more demanding than the last one, and I'll say that, let me ask this question. Do you think that this last homework was easier than the one prior? Okay, I think this next homework is probably even easier, okay? I'm not saying it's shorter, but it's probably of the same length in terms of calculations, but it's very straightforward, and you'll see what I mean after we get into our topic today. As of now, everything that was outstanding is graded. Obviously I haven't graded 2.2 yet because it was due today. But 2.1 is graded. For the most part, everybody did pretty well. I think that, again, I think that 2.1 assignment was a little challenging in terms of getting the figure right. But I think you'll find that our, better method of doing things using IJK notation will resolve any confusion. And it'll be a lot more straightforward, a lot more systematic. And we'll see that adding 7 vectors is easier using this approach than maybe adding 2 vectors using a graphical approach. Okay, everybody get the QR code? I see a couple people saying. Everybody get it? We good? All right, okay. All right. Okay. So I went through a lot of this last time. I'll go through it briefly again. I know you all have other classes besides this one, so a nice little refresher isn't exactly the worst idea in the world. But I don't think that we're going to be here very long. I mean, I don't think we're going to be here the full 50 minutes because we'll get into our example, and I don't think our example will take the whole time. So again, star of the show is vectors. Remember, vectors contain magnitude and a direction. We can multiply vectors by scalars to change their magnitude. We won't change their direction by doing that. The only thing that we can do is multiply a vector by a negative number and it flips the direction. When we add vectors, we do add them in a graphical tip-to-tail fashion. And whether we do it using this graphical trigonometric approach that we've been doing up until now or using IJK notation, we still add vectors the same fashion. IJK notation just allows us to describe vectors in a systematic fashion so that the adding process is much more natural. Okay. Oh, and again, vector addition is commutative. So vector A plus vector B is the same thing as vector B plus vector A. The order of operations doesn't matter. Yet for vector multiplication, or specifically the cross product, that does matter. The order of operations does matter. Okay. All right. So what we want to do is we want to take all this graphical hullabaloo, this sort of picturesque way of adding vectors, which I think is good from a conceptual standpoint. I'm sure that some of you have probably felt that some of the math that we've been doing on the last couple of examples has been cumbersome, but I think you probably agree at least the picture that it's painting is pretty easy to understand. But we're engineers and we need to perform computations and we need to do it in a systematic fashion. Okay, so I want to describe vectors systematically. So what I'm now going to start doing is thinking about vectors in terms of their Cartesian components. In other words, I can represent vector f by saying vector x plus, or vector f in the x direction plus vector f in the y direction. So take the vector and project it onto either the x and y axes and just sum up those components. And again, vector addition is commutative, so I could say vector fy plus vector fx, and I would still get the same tip to tail for the original vector. So it's a very useful way of describing vectors is to split them up into x and y components. Okay, and so that's what we're going to start doing. And the main reason for that is that if we describe vectors based on their x and y components, it's really easy to add them up. See, if you have a bunch of vectors that are all pointing the same way, you can add the vectors up by just adding up their magnitudes, okay? Because tip to tail, you're just stacking them along one another, okay? that only works when the vectors are pointing in the same way. So if you can describe every vector with an x component and a y component, you can just add up all the x components, add up all the y components, and the vector addition is done. So it's very, very, very systematic. Okay? And so that's why we're going to describe vectors this way. Now we have a subtle nuance to the notation that we're going to use, and this is where the ij part comes in, and that's where we employ the use of unit vectors. Okay? So remember, a vector is described by both its magnitude and its direction, or orientation, or however you want to describe that. Magnitude and direction. Well, what I'm going to do is, since multiplying by a scalar only changes the magnitude, I can sort of think of that in reverse and go, well, what if I factor out the magnitude? So I propose some arbitrary vector with a magnitude and a direction. If I factor out the magnitude, I have the magnitude out here, and then what I'm left with is a vector that has a magnitude of 1. The direction is still preserved, but the magnitude is just a single unit. It's just 1. And so any vector with a length of 1 is a unit vector. Okay? Unit vectors are really, really important for helping to describe just direction. So it's a really convenient way of separating magnitude and direction when you're trying to describe forces and what have you. And we're going to use unit vectors quite a bit later. We will have generic unit vectors, like a unit vector in some arbitrary direction, but the most useful ones, or the most commonly used unit vectors, are our essential basis unit vectors, I, j, and k. So I, j, and k are just unit vectors that point along the positive x, y, and z axis. So the thing about that notation is that it is pretty ubiquitous in all areas of mathematics and physics. So if you ever see a vector written in this fashion, so for example, if I were to talk about vector 3i plus 4j, whether we're in a Math 229 class or a Physics 211 class or an Engineering 213 class, everybody sort of understands that notation. It's pretty common among anybody in exploring these types of disciplines that we all understand what that notation means. So that's one of the reasons that it's employed, is that it crosses various disciplines and we're all speaking the same language. What we're going to do for now, since so right now we're still operating in 2D. So the idea behind what we're doing in this first unit in the class is we learned about vector addition using essentially pictures and trig, and then I think we pretty quickly discovered that that's kind of cumbersome, and so maybe there's a more systematic way of doing it, and so that's what we're doing here. Once we get that systematic way down pat, we'll realize that 2D and 3D really aren't that different. And so we'll be able to extend these computations into the third dimension without really any real additional difficulty. So that's sort of the theme of what we're doing. So we're starting in 2D land. Now, I, j, and k are defined in their positive direction. So if I say the I vector, it is defined along the positive x-axis. The j vector is defined along the positive y-axis. That's how we identify their base direction. So here's going to be sort of our standard notation. So whenever we describe a vector, and I think I have a slight little typo here because that should be bold. I'll fix that later, but that should be bold. Whenever we have an arbitrary vector, what we're going to do is say that vector as described as a pile of junk times I plus another pile of junk times j. And what those pile of junks are the respective magnitudes along the x and y axis. And so by multiplying them by I and multiplying them by j, what we're saying is this is the magnitude along the x-axis for I, because that's what I is. I says that is the direction. The direction of the I vector is along x. The direction of the j vector is along y. So that's how we get our magnitude and direction. Okay? So now the formula that I'm writing here, f cosine I and then f sine I, assumes that the angle is measured from the x-axis, because trig, cosine, and sine, x and y. That's pretty easily navigable as long as you got a good basis on what you're doing. That's usually not too terribly cumbersome. Okay. We're going to do a couple basic problems. So the first thing we're going to do is just make sure that we're comfortable describing a single vector. Then we'll get into something a little more fun, which is adding some vectors. So let's do the first one first. Let's go to our first example. So I have a vector here. I want to describe this vector in IJ notation, okay? Now, in order to describe this vector, I want to make sure that we all remember things about graphing functions. So if I have a coordinate system right here, this is the x-axis, this is the y-axis. Do you all remember this stuff? Y'all remember that? What do those mean? Like, why did we start, like, when we started saying quadrant 1, quadrant 2, quadrant 3, quadrant 4, like, what does quadrant 2 mean? Like, what, if you were to describe that to me, how would you describe quadrant 2?
Negative x value and positive y.
There we go, right? That's why we say that, because anything in quadrant 2 has a negative x value and a positive y value. Anything in quadrant 3, both values are negative, right? So whenever I first start showing students how to do vector calculations, I kind of want to start with this just to make sure that, look, we're going to do a bunch of calculations, but at the end of the day, I just want to make sure that what we're putting in the answer box just reflects what's going on. And let me show you what I mean, okay? So I have here an 800 Newton vector at an angle of 35 degrees, okay? So let's just keep this basic, okay? Okay, so I have a right triangle, okay? This is 35 degrees. This is 800 newtons, okay? Could somebody tell me how long this is? Just the leg of this triangle. How long is it? How would you calculate how long this is? Exactly right, 800 cosine 35. So we'll call this, I don't know, fx. Let's call this fy. So fx equals 800 newtons cosine 35 degrees. What is the answer here? Second on that? Okay. All right. So Fy is what? 800 newtons times sine of 35. Which is?
458.86.
Do I have a second? Okay. So if I were to describe this vector in IJ notation, would this be the answer? Hold on, let me finish writing it. Is that the answer right there?
No.
No, it's not. Why?
Because it's going in the negative x direction.
This is negative. That's exactly right. Okay. And so the point I'm making here is, let me sort of box this up. The point I'm making here is I think it is very convenient as a student to go, okay, this is 800 newtons, this is 35 degrees, so just sine and cosine will get you your x and y components. That's easy calculation. We can chug that out 100 times, it's no problem. But at the end of the day, it is very easy in these problems to go from this to this and not put that negative there, okay? And so the only thing I'm saying is this vector is in quadrant 2. The x component's negative, the y component's positive, right? Just make sure you get the signs right, okay? Does that make sense? You're going to have problems like this, and I mean, I've been teaching this class for a while. I know that there will be somebody in here that forgets to put that negative there, okay? Just remember that. Okay. This isn't bad, right? This is simple? Okay. I'm going to show you something. Maybe we'll do this later. I'll look at this later, how you can even do some of these problems in AutoCAD if you want, but we can do that later. All right, so, okay. All right, so now what we're going to do is we're going to do this problem, okay? And prior to the imposition of an IJK notation, this problem would be pretty cumbersome, because what I would have to do is I'd have to take two of these vectors, add them up graphically to get a resultant using trig, like law sines, law cosines. Then I would have to take that sum, add it with the third vector, and do another triangle solution. It would work, it'd give you the answer, but it would just be a pain. It would just be very difficult, okay? Instead, IJ notation is going to make the solution of this problem really, really easy, okay? Now, let me show you what we're going to do, okay? The first thing I'm going to do is I'm going to start naming these vectors. No real necessity to do that, just so that when we start doing problems in here, that we're all saying the same thing. So we will call this vector A. Let's call this vector B, and let's call this vector C. Just so when we start doing calculations, we're all good. Okay. Now, what we're going to do is sum up these three vectors into a single resultant. Okay. Now, one thing that's different from this problem as opposed to the last one is the last one we were given an angle of 35 degrees, right? We were not given an angle in this problem. Instead, what we were given is, like, if we look at vector A, we just know vector A is along this line, and the line is defined by this 84 inches, okay? So what that means is we're going to have to figure out the angle from this and then start doing the trig. So let me walk you through vector A first. Let's do vector A. Okay, so what do we know about vector A? Vector A is going about like this. Here's vector A, and we know that it exists in this box where this is 80 inches, this is 84 inches, okay? So maybe what I'll do is I'll try and figure out this angle theta A. Let's try and figure this angle out right here. Because then I can figure out that angle and take sine and cosine of the 29 pounds to get the x and y components. So somebody help me out. How would we calculate angle A? What is angle A? How would we do that? What's that? Tangent, or more specifically, the inverse tangent. Because the tangent of the angle is what? What's the tangent of this angle? Say it again?
80 over 84.
The tangent is 80 over 84. So the inverse tangent of 80 over 84 will give us the angle, right? Okay, and so what do we get here? Let's say 2 decimal places. 44.64. 43.60. Everybody else got? Okay, before we move on, okay, I just want to mention something. So if I have a right triangle that has one leg that's 3, one leg that's 4, what's the hypotenuse? 5. It's a 3, 4, 5 triangle. It's a special triangle such that the hypotenuse has a nice even number, right? There's a lot of triangles like that. I mention that because some of the calculations that we do in this problem, you're going to get these, like, nasty angles, but when we take sines and cosines, it might come out as pretty simple numbers, okay? So, therefore, if I wanted to find the x component, I would say the x component, so how would we find the x component of the force, right? Well, I would take 29 pounds times the cosine of this angle, right? And then 29 pounds times the sine of the angle for the y component. So we'll say 29 pounds. By the way, if you see this in an engineering computation, that pound symbol or that hashtag symbol, that used to be the pound symbol. So sometimes you'll see engineers use that for pounds. So what does this come out to be? 21. It actually comes out to be exactly 21 pounds. What about this one? £20. So therefore, could we describe vector A as 21 pounds times I plus 20 pounds times J? Is that a fair way of describing that vector? Are the signs right? They're both positive, right? Because that's a quadrant 1 vector. So I'm going to just sort of box this and say, there's a description for that vector. With me so far? So we just keep doing the same thing. We just do the same thing for vector B, do the same thing for vector C, and then we got 3 vectors that are all written with the standard notation. We can just add them up, easy as could be. So 28. Okay, so let's look at vector B. And if you need me to scroll up and down or anything, you let me know, okay? So vector B is going to be a vector, it kind of points like this. And we're given that this dimension here is 28 inches. This dimension here, 96 inches. So that's what we're given. Tell me what to do. You tell me. Which angle do I want to solve for inside this triangle? The one up top or the one on the bottom? Exactly right. That's my theta, by the way. So how do I solve for theta B? What is the answer? What is theta B? There you go. Inverse tangent of 96 over 28. And what does that come out to be? I think that was seconded. All right. So therefore, if I want my components, so that's going to be, what was that? That was 50 pounds. Yeah, get ahead of myself. All right, so what do we get for each of these? I heard it. That was the second, right?
Yes, it was.
Okay, so vector B, that means it's is that right? Negative 14. That's 100% right. So I'm making sure everybody's awake. What do we think? So far, so good? Okay. So vector C, let's scroll up here. Let's see how vector C is. So vector C is pointing this way. That's 48 and that's 90. So better than that. Let's do about like that. Okay, so the x dimension, that's 48. That's 90. Which angle do I want? Top one. I want this one. So what do we got? We've got the inverse tangent of what? And that comes out to be, see how this just seems a lot easier than doing all that other stuff? Again, I think that other stuff's necessary to understand the idea, but when it comes to execution, this is just a lot more elegant. So this is, what was that, 51 pounds? Okay, and so what do we get for x and y? 24 and 45. Do I have a second?
Yep.
Okay, so therefore C is there's that. What's wrong with it? There you go. See? I'll tell you this, there is also kind of a reason I like to contain my signs inside the parentheses. There's just sort of a reason I like to do that. For me, I find it easier visually to add the vectors, but we're going to get to that here in a second, okay? Is everybody with me so far? Now, in order to compute the resultant is adding the vectors, okay? So let's just sort of write these vectors top to bottom. So we have vector A, vector B, vector C. So we've got 21 times I. We've got negative 14 I. We've got 24 I plus 20, 48, and negative 45. I can do better than that. Okay. See, I like to keep my signs contained inside the parentheses so that when I'm doing the addition, I can just look inside the parentheses and make sure that everything is right. That's just my way of doing it. All right? And so what we're going to do is we're going to add these up, and we're going to add them up. You know, the way you've done this type of stuff before. So we'll just say that the resultant vector is just the sum of the individual vectors. And so what do we get? Okay, what goes in here? Well, it's 21 minus 14 plus 24, which is 30. 30 or 31? I plus, and what goes here? What is that, 23? Yeah, because 48 minus 45 is 3, so that's 23. And so, what's my resultant vector? It's right here. Bless you. Now, we're not finished yet because I got a couple other things I want to look at. So first off, this is a perfectly acceptable way of describing the vector. And in my opinion, that is sort of a way you could end the problem right there. Often, though, we are interested in finding out more things about said vector, such as the magnitude and direction of that vector. One of, I guess, the downsides of this notation is that it only gives you the magnitude along the x-axis or the magnitude along the y-axis. How would we find the magnitude in general? There you go. So I propose that just r, which is the magnitude of the vector, is just use the Pythagorean theorem. So and so what do we get for this? 38.60. Do I have a second? We're doing good on time. All right. What about the orientation? How do you think we could find the orientation? First off, what quadrant is this vector in?
Is it 1?
1, yeah, because it's positive x, positive y. So if I wanted to find this right here, maybe the orientation of the resultant, how would I do that? The same way I've been doing it this whole time. And so maybe what I'll do is I'll say that that is that, and what do we get?
36.57.
Degrees, right? So another way of writing this vector would be this. That would work too, wouldn't it? Suddenly adding like a bunch of vectors doesn't seem as daunting. Granted, I get that the calculations are monotonous, but if they're boring, that means you've learned something, because then you know how to do it, you know? Take a step back. Let's see if anybody has any questions. Everybody good? All right. So I'll show you. This is, by the way, this is the last homework I'm going to put a picture on the homework assignment. From here on out, I'll probably just assign the homeworks directly. But this is let's see, we're on 2, 3. Yeah. So I'm giving you a series of vectors. Just basically do what we've done here, right? Add them up, give me the resultant, give me the magnitude and orientation of the resultant. Pretty straightforward. Not too bad, right? Hopefully this homework is boring. If it is, then you're comfortable with this topic. Sound good?
Yep.
Would you like 15 minutes back of your life? Especially for the 3-day weekend. That's all I got, everybody. I'm going to pull up the code one more time. You all have a wonderful weekend.